In a previous video, we developed the mathematical representation of the vertical and the horizontal components of a dipole. We found that they varied as inversely as the cube of the distance to the center of the dipole. We have the magnetic dipole moment here, P times L, the length of the dipole, the pole strength times the length of the dipole. Over here for the horizontal field, just the dipole moment times the sine of theta. So we ended up with these expressions here. Now, these expressions come for the case when the dipole is very, very, very far away, so that r plus and r minus are just a little bit different by the amount dr, depending on the inclination of the dipole. So now we're going to take a look at the case where the dipole, we're pulling a dipole up, it's in the near surface. We have to consider the negative and the positive pole separately. Their contributions have to be considered, well, they were considered separately in the previous case, but we ended up with a simplification there that we won't find here. So let's take a look at how we go about working through that problem. And so in this case, we have the magnetic field intensity from the positive pole is equal to minus p over the distance to the positive pole. Remember, upward pointing vectors are negative. The magnetic field intensity associated with the negative pole is positive, the pole strength over the distance squared. So just keep the conventions in mind as we work through this. Now, using the relationships that we have over here, we've got the observation point located here. This is the distance from some arbitrary origin for the x-axis. This is the depth beneath the surface. So these would be the distances, the x distances, and the depths, the z distances to the negative and the positive pole. We also have to consider these angles. The angle made with the negative pole, the angle that the observation point makes with the positive pole, because we're going to be resolving the individual components, f minus and f plus, with respect to the vertical or the horizontal. So the magnetic field intensity associated with the negative pole would be equal to the magnetic field intensity of the pole times the sine of alpha. So we have to take the projection. We have to take the sine of alpha minus. So we have to take the vertical projection of the magnetic field intensity associated with this pole. We have to do the same, take the projection, to get the magnetic field intensity associated with the positive pole. So we have f plus times the sine of alpha plus. And the same for the horizontal components, except we're looking at the cosine terms. And we have the magnetic field intensities for the positive and negative poles times the cosine of alpha minus and cosine of alpha plus. So in general, sine of alpha, whether it's plus or minus, would be z over r, and the cosine of alpha, x over r. So, as an exercise, make the appropriate substitutions and proceed on determining the vertical and horizontal components of the dipole. Now, if you do that, you're calculating the magnetic field intensity in the z direction, and so we have f minus times the sine of alpha minus, and that gives us p times z over r cubed. Remember, z minus over r is going to be the sine of alpha, so we have p over r times the sine of alpha times, or p over r times z minus over r. And if we express r explicitly in terms of x and z, we have x0 minus x minus the quantity squared plus z minus squared to the 3/2 power. And then we could do the same thing for the positive pole. Positive pole over here. Calculate the field intensity associated with the positive pole. And then we come up with a similar expression We do have this negative sign in here because of our conventions for negative and positive vectors, vector field intensities. So don't forget that when we're dealing with an object, this could be a buried drum, so it might have some cross-sectional area, storage tank, propane tank, some other object, unexploded ordnance, and it will have some susceptibility. So in working with problems of this nature, we may have information related to the geometry of the object so that we know what A is, and this term may be a good substitute for the P's in the above relationships. Now down here we have, once you get to the negative and the positive components, the negative and the positive contributions to the vertical field intensity of the dipole, you sum them together in order to get the anomalous vertical field intensity. You do the same with the components for the horizontal field intensity. So we just sum those together, and then we know that the anomalous field intensity, or perhaps F sub AT, should just be equal to the square root of the sum of the squares. So you should be able to use Excel or MATLAB. I would note that Excel files are provided in Berger et al.'s text, as we did noted before. And in this particular case, we have X, the origin, located right in the center of the dipole. So now the plots, as you'll notice here, aren't symmetrical as they were. The vertical component is not symmetrical as it was for the monopole. It's a little bit offset to the south, and that's because for both the vertical and the horizontal components, we're dealing with two poles now, one of which is closer to the surface and has a larger influence, in this case the negative pole, than the positive pole. So we see it, but again we see this kind of asymmetry going off to the north. And again, I didn't put my directions in there, but the directions are here. And notice again that for the horizontal component, this is negative because the vector orientation of the horizontal component is pointing to the south. Once we get to a point beyond the center of the dipole, if we go in the other direction, the vector field, the horizontal field intensity is pointing to the north. So those would be the conventions for the monopole and the dipole. And remember that the asymmetry in this case is associated with the fact that the negative end of the dipole is closer to the surface than the positive end. So over here, when we're looking at the dipole field, we get this asymmetry, and the sign conventions that we're using make this a negative to the north. So we see this general dip because the total field intensity, anomalous total field intensity, is just the square root of the sum of the squares here. We're going to see it also dip to the north. In addition, again, just to be redundant, the vertical component for the dipole field is not symmetrical as it was for the monopole field. So next time we're going to take, I'd give this a try, putting this into Excel, or hunt these. Perhaps there are some Excel files out there on the internet, but we're going to take a brief look at some different types of magnetic materials in the next video. Maybe a little bit out of sequence, but now that we've talked so much about magnetic fields and what they are, what they look like, we'll come back and talk about very briefly about the different kinds of magnetization that we encounter. So talk to you then, and thanks for joining us.